So for the second keynote, we're going to have Dr. Ricardo Vinuesa, who is an associate professor at the Department of Aerospace Engineering here at University of Michigan. So he's a pretty unique case because he's both internal and external speaker at the same time, because he recently just moved from KTH, Sweden, after spending 11 years of his time before joining University of Michigan this year. He studied mechanical engineering at the Polytechnical University of Valencia, Spain, and he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand, control, and predict complex wall-bounded turbulent flows, such as the boundary layers developing around wings and urban environments. So we're very excited to hear about it. Thanks.
Thank you very much for the introduction and also for the invitation. It's a great pleasure to be here. And I'm going to be speaking about how to improve turbulence control. And I know that in the audience there's a lot of people who are not so familiar with turbulence, so I will try to kind of make it accessible to everybody through explainable deep learning. So we're going to try to bring a bit of a physics perspective to ML and try to really find impactful applications here. And this work is funded mostly by the ERC, the European Research Council, back in Europe. So let me first figure out this. Okay. So let me first thank my collaborators. These are just some of the people who have made this possible, and just few of them, because I cannot list everybody. There's, of course, multiple students, postdocs over the years who have really been great and have enabled all this research that I'm going to be talking about today. So thanks to them, and let me start with a short motivation. When I talk about control, I'm looking at this type of complex flows. Let me show you a little video. So we have been doing a lot of computational work before the ML work on computational fluid dynamics. So what you can see here is a turbulent wing, so the wing of an airplane, where we cut and have a rounded wing tip over here. And what I'm showing you are vortices, vertical motions, swirls present in the flow. And I'm going to be telling you a bit more about it later. This is the highest resource simulations that you can have. We're solving all the scales. We have a Reynolds number of 200,000, which is kind of similar to what you can do in a wind tunnel. And we really have a high level of detail, as you can see. You can see how next to the wing tip, the pressure difference, so basically there's higher pressure on the lower side of the wing, creates this vortex, this motion that rolls around the wing and is impacting the aerodynamics that happens in the wake. So that's after the wing. So essentially, this rotational motion here, what it's doing is making it more difficult for the wing to extract lift from the air around it. You need to increase the angle of attack to get the same lift, and that adds an additional component, which would be the lift-induced component of the drag. So basically, this very chaotic motion over here, this is what we call turbulence. And this chaotic motion, this very multi-scale and intricate motion, this is what we are trying to answer and try to really get into some of the details in order to reduce drag, in order to enhance mixing, and improve a wide range of applications that we have around us. So we're going to be, and by the way, remember that I'm showing you vortices. Every time that someone does a very nice simulation on hundreds of thousands of processors, they're showing you typically vortices. And at the end, this is something that you can see when you do a wind tunnel experiment, but nobody tells you that this is important in your flow. This is something that you can see. Keep this idea in mind, because we'll get back to it later in the presentation. So for now, just keep how complex these flows are and how chaotic all the motions look like. So if I want to control, and by control what I mean is to, for example, reduce the drag, so the friction of the air around the airplane, I may do that in different ways. Let's imagine that I have this instantaneous 3D object, and this could be these vortices that I showed you before. One possibility to control the flow could be to first identify what are the most important regions. So out of those 3D objects, which ones really matter and which ones do not matter. So first identify the most important regions in the flow. And second, once we identify the important regions, just eliminate in a very surgical way those important features and nothing else, so that I can have a very targeted, a very efficient control, just focusing on the most important regions of the flow. Okay? So that's going to be the guiding principle for the rest of the presentation. I'm first going to identify the most important of those 3D objects, and second, we're going to try to control those. And to identify the most important, we're going to be using explainable deep learning. So we're going to try to use some ideas of really assessing causal mechanisms present in our complex turbulent flow. And this question, what are the most important features of the flow, this has been asked in the past. For example, Encinar and Jimenez, they tried to look at this question by doing interventional causality analysis. So basically, they would simulate the flow, introduce a perturbation, resimulate it, and then see which of those perturbations were growing the most. And of course, they got some interesting conclusions, but this is interventional, meaning that you're basically changing your flow. And this is very computationally expensive because you need to rerun many simulations. An alternative path was taken by Lozano Duran and Aranth, who used information theory and causality in a non-interventional manner. So basically, they would create time series using PCA or similar methods, eliminate one time series from the prediction, and see how that removal would affect the predictions of the rest of time series. And working like that, they would create causality maps like this one to try to see where the energy is coming from and where it is going, basically. So these are both ways to try to understand a bit how turbulent flows work. The approach that we take is kind of in the middle. We want to do an interventional method, but on a surrogate model, meaning that we are not going to resimulate the flow. Since we do it on a surrogate model, we're going to stick to the original trajectory. We're not going to go to different trajectories, but we're going to try to remove elements to see how that affects the predictions in our system. So we start with this example here. This is the flow between two walls, basically. This is a turbulent flow in a turbulent channel. We're going to identify 3D objects like this one, which satisfy this condition. This condition means that you have what is called an intense Reynolds shear stress. So basically, you have regions of strong fluctuations in the direction of the flow and in the vertical direction. And those regions, I can tell you that this is something that traditionally people have been thinking that is important, and now we're going to try to really assess if this is important or not using explainability. So once again, and this is kind of like the theme of this first part, the classical intuition is not always right, especially in this very complex multi-scale phenomena. So let's look a little bit at the method, and this is something that we published with Andrés Cremades last year in Nature Communications. We basically have 3 steps. So we are going to try to use Shapley additive explanations, SHAP analysis, to, given the state of the flow, the present state of the flow, which consists of three-dimensional fields, the UV and W fluctuations, we are going to predict the future state of the flow, so the UV and W fluctuations in the future, and then we're going to identify these volumes of Reynolds stress, of U and V fluctuation, and we're going to remove them. Right? So we're going to do the SHAP analysis, so we will remove this big volume, repeat the prediction. If the error of the prediction increases a lot, that means that this volume here was very important. If the error doesn't change very much, that means that this was not very important, in a nutshell. Okay? So working like that, what we're going to do, and we first need a prediction method to go from the present state to the future state. Here we use a UNet. We can use many different methods. We have used diffusion, but in this particular case with a UNet, we got very good accuracy, less than 0.5% error in our predictions. And essentially, the key ingredient here is how far away the input and output data are. So remember, the input is our present state, the output is our future state, and that time delay between input and output will determine the time scale of the features that we're going to be identifying in our problem. So we took a range from 1 to 10 viscous units. Viscous units are the temporal dynamics of whatever happens very close to the wall. And we're interested in that because, remember, we want to do flow control, so we want to reduce friction in the end. And the results that we got were basically the same. So we got the same features of importance for that range from 1 to 10 viscous units. So this unit, again, this is just a computational tool to then use explainability on top of it, diffusion, flow matching, other methods that we've been trying that would give us another means of performing that prediction. So we have this computational framework, and this is how the algorithm would go. So I would have the present state of the flow, which are the fluctuations now. These are three-dimensional fields of U, B, and W. U mean streamwise fluctuation, flow going like this, V flowing going up, W flow going sideways. So we have three velocity components now. I will predict with the unit a future state of the flow, again, with a time delay associated with the temporal dynamics that I want to resolve. And then I will compare the prediction with the ground truth. And the ground truth comes from very, very highly resolved numerical data. So this highly resolved numerical data is used both to train our models, but also to kind of validate these predictions. That's where we get less than 0.5% error, with maximum errors below 1%, by the way. So in regions of high fluctuation, we also get very high performance. And that's the prediction error that we have. Then we go back to here, to the input data. We segment the flow with those 3D volumes. Now we remove one of those volumes. I repeat my prediction, and I recalculate the error. And if the error increases a lot, that means that that volume was important, and vice versa. So essentially, for each of those 3D volumes, I get a sharp value or importance score that basically tells me what is the capability of prediction of future states of the flow of that region, of that volume that I have there. And I'm sure many of you are familiar with SHAP, but just a quick recap. This is basically a linear model of the error between the neural network and the ground truth. So this is a superposition of features. Q1, Q2, Qn, these are binary variables that indicate whether the structure is present or absent in my flow when I perform my prediction. And this phi1, phi2, phi-n, these are weighting factors that represent how much that structure contributes to the error. These are basically the SHAP values. So these are the importance scores. So in the end, the problem reduces to just solving this square regression, where I want to minimize the error between the linear model and the actual prediction. Right? So my neural network will have an error with respect to the ground truth. I want the linear model of that error to be as small as possible, basically. And this pi x, this is a kernel based on game theory, which creates coalitions. I'll tell you more about those coalitions in just a second. So there's two main assumptions here that we want to really get out of the way before using this for turbulent flows. The first one is, look, I have a complex flow, which is chaotic, which is nonlinear, with all those crazy, complicated interactions that I showed you in the video. How is it that now I'm using a linear model to reproduce the error of that system? And the reality is that I have hundreds of these features per snapshot, and I have on the order of 10,000 snapshots. I have many, many of those features. So the linear superposition of all of those is kind of like a leading order expansion of all the possible contributions to the error. That linear model gives me a deviation with respect to the two error of 10 to the minus 7, where we are looking at order 1 quantities. So in principle, this linear model is sufficient to reconstruct the accuracy of this nonlinear problem, because I have literally hundreds of thousands of features, basically. Second, and perhaps more critically, again, I have a quite complex nonlinear flow, which is interacting, and then I'm removing things. Am I removing them one by one? Is that a fair way to really assess the dynamics of this complex flow? The reality is that it's not exactly done one by one. It's done through these kernels that are selecting coalitions. So each feature is removed in a context, together with other structures around it, sometimes close to the wall, sometimes farther away from the wall. And the net contribution of each feature to the error is assessed in many of those contexts. So this emulates the interscale interactions that you have turbulence, because each structure is contributing with many others, and that basically reproduces quite well the dynamics of our problem. So we have tested this for many different numbers of coalitions, structures per coalition. The results are robust and converged. So we're pretty confident that this approach with the kernel of coalitions is giving us a good representation of the causal mechanisms in our problem. So having looked at this, what we know is that we have a method to assess importance of each of the 3D volumes that we have in our system, basically. Now let's look at some results. What I'm showing you here is the joint PDF, the joint probability density function of the structures in the flow. The vertical axis is the importance, that's the absolute value of the SHAP score, and the horizontal axis is the volume of the structures. And in principle, what I see is a pretty good correlation. So larger structures have more importance, which in principle, that's not very surprising. I can divide them into different quadrants, which have different physics. I will not get too much into that, because that's maybe more for the turbulence community. But just to get the idea that ejections, which is flow going away from the wall, that's the one with the highest importance over here. And that's when I look at the importance in a raw sense. When I scale the importance per unit volume as a function of the volume, then things change. When I have kind of like a specific importance, the largest objects over here are not the most important anymore. The most important are these ones over here, which are medium-sized ejections. So smaller objects that, again, go away from the wall. And that's, again, that starts to be a little bit against the intuition, the classical intuition. We are starting to see things that are a bit different from the classical understanding of these types of problems. Now, let's look at these 3D volumes, the physical characteristics that they have, which is the Reynolds shear stress. This Reynolds shear stress, once again, is a correlation between flow going forward and flow going up. If I plot the importance as a function of that Reynolds shear stress, what I see is a good correlation. So in principle, these 3D volumes with higher Reynolds shear stress, which is the quantity that people have been looking at, exhibits a good correlation with importance. But if I scale the importance per unit volume and I represent that as a function of the Reynolds shear stress per unit volume, again, the quantity that people have been looking at, what I see is a lack of correlation. Now I see 3 different areas. In this first area, you can see a pretty broad spread of important values, so the correlation is gone. In region B over here, you can see the structures with the highest Reynolds shear stress, and up here, the structures with the highest importance, and they're not the same. So now we start to see that the classical understanding of what's important and what is not necessarily true. Here are the things with highest importance. They're not the ones with the highest Reynolds shear stress. This is one first result that is interesting in the context of how we can interrogate the data to tell us what matters and what doesn't matter, and not necessarily rely on the classical intuition. Of course, one advantage of this method is that it can be applied also to experimental data. And this is a wind tunnel experiment by my friends at the University of Melbourne. This is Ivan Marusik's group. The reason why I want to do this experimentally and not only numerically is twofold. The first one is an experiment can be done in more extreme conditions than a simulation. So if I identify what's important in a very small simulation, that might not be the same as in a very large experiment, first of all. And second, and more crucially, even if I could do a simulation at the same conditions as those in an experiment, the simulation will have much higher resolution than the experiment. When you're measuring, you have noisy data, low resolution, inaccessibility to certain areas. So the very nice 3D volumes that I showed you, you will not be able to find them in a wind tunnel experiment, just because of the lack of resolution and quality of measurements. So the question is not, what are the most important structures in the flow? The question is, from whatever I can measure, which may be limited, what is the most important? And that's why I want to apply this framework directly to experimental data sets. And the framework there in Melbourne was very similar to that of the simulations. The Reynolds number, which tells me how chaotic my flow is, so how challenging the situation is an order of magnitude larger. So that's a more challenging case. But in terms of time resolution, it's very similar. The main difference is that experimental data is two-dimensional. So you cannot look at 3D volumes. You can only look at 2D planes, basically. And you will have lower resolution than in the simulation, basically. The results look actually consistent with those of the numerical data, which is reassuring. We're getting the same in the simulation, in the computer, and in the big wind tunnel. If I look at the importance as a function of the surface of the structures, I still have a pretty good correlation. If I scale the importance per unit surface and represent that as a function of the surface, I find again that the largest objects are not the most important anymore. the most important are medium-sized objects that are coming away from the wall. And if I look again at the Reynolds shear stress, I find something quite consistent. What I find is a very good correlation between the importance and the Reynolds shear stress. And if I scale the importance per unit surface as a function of the Reynolds shear stress per unit surface, the same three areas that I found before are also present. Region A, where the correlation is gone. Region B, where the Reynolds shear stress is dominant. And region C, the structures with the highest importance. And now, experimentally, we get the same as with the simulation. We corroborate that the classical intuition might not be the best, because the most important structures which are up here are not the ones with the highest Reynolds shear stress, which is the quantity that people have been looking at. So here's where we start to get some intuition. But of course, everything that I've been telling you so far was with an initial assumption. I was pre-selecting those 3D volumes, and I was telling you, OK, this is important, this is not, whatever. But I was pre-selecting those. Ideally, what you would want to do is calculate the importance of each point, and then cluster the regions of highest importance. And that's something that we did for the experimental data. Let's see if this works now. Yeah. Using gradient SHAP, which is a variant of the Shapley framework. This is much more computationally efficient, and it essentially allows me to formulate the problem similarly. So my input will be the velocity now, the fields of velocity now. My output will be the fields of velocity in the future. And now the difference is that I'm going to be removing the points one by one. So I take this point over here, I remove it. If the error increases a lot, that means that this point is very important. If the error doesn't change very much, that means that that point was not very important. So gradient SHAP conceptually is similar to kernel SHAP, which we used before. The computation is much more computationally efficient, and it allows us to calculate the importance point by point. So now, it's a complete change of paradigm. I'm not going to pre-select any volumes. I'm just going to look for experimental data at the importance of each point of the domain. And remember, the experiment is 2D, so this is a 2D slice. In black, I'm showing you the classical structures, and in green, I'm showing you our structures defined purely based on importance. How do we create those 2D surfaces? Through percolation analysis. So basically, we retain the regions of highest importance, and we create a percolation threshold to select and create those regions of highest importance. There is 70% agreement, there is 70% overlap between our structures purely based on importance and the classical ones, which is a reassuring message. That means that the classical ones were not so wrong, but they were missing part of the story. And this is the end of our paper last year, but we were not completely satisfied. We wanted more answers. So what we did was to scale up the gradient SHAP to the numerical data set. And now this was computationally very demanding because the computations at quite high Reynolds number, we're talking about 500-600 million grid points per snapshot, 10,000 snapshots. Calculate SHAP, you need to do a lot of these coalitions. This was computationally very demanding, but we managed to do that and basically extend the analysis to the numerical data set. So, and this is just accepted in Nature Communications. This is a follow-up to the previous study. You're going to see this is quite cool when you look at things numerically. So what I'm showing you are 3D snapshots of different objects. Remember the video that I showed you with the wing and the 3D objects? These are the different things. What I showed you were vortices, and these guys over here. This is one of the structures that people have been looking at classically. These Q events, this is what I showed you in the first part of the presentation, the correlation between U and V. And streaks, this is another thing that people have been looking at classically. These are regions of high speed close to the surface of a wing, basically. In the top left corner, I'm showing you the SHAP-based structures. So these are three-dimensional regions where the importance is very high, importance measured by the SHAP value. And we do percolation analysis for each snapshot, and then we get instantaneously these guys over here, which intuitively they look a little bit like these Reynolds stresses, but they're a bit different. So just to kind of reiterate a bit, these ones over here are the ones that we identified based on importance. And the three others are classical views of turbulence. To give you some background, turbulence is an unsolved problem of physics for over 150 years. People have been going a bit in circles, looking at the same things. So we're trying to bring in a new perspective to an old problem, basically. Okay? So what happens when we look at the statistics of all these guys? Because if you remember the video, things were very chaotic and unsteady. The only way to understand things is to do a statistical analysis. So I'm showing you here the PDF, the joint probability density function, of, in this big panel, I'm showing you the SHAP structures. So this one's based on importance. The vertical axis is the distance from the wing surface. So if you go higher up, that's a larger value of the vertical axis. And the horizontal axis is the intensity of the fluctuations in the streamwise direction. So how turbulent the motions are, basically. Okay? So these are my structures that I identify based on importance. And in here, I'm showing you the same PDF for the classical ones. So at the top, Reynolds stresses. At the second row, streaks. And the last one is the vortices, what I showed you in the wing video. Okay? So I'm comparing my importance-based structures with classical ones. And if you look at them, they're different, but there seems to be some similarities. Let me guide you a little bit so you know where to look at. This region over here looks a little bit like that region over there, and that's flow that is going towards the wall. These are called sweeps. This region over here looks quite a bit like that one over there. That's the flow that goes away from the wall. I was telling you about it before. That's called ejection. So there is a bit of similarity, close to the wing surface, far away from the wing surface. If we look here, this is a region that is called the near wall region. You can see quite some similarity between this and that. That's a low speed streak. And between this and that, that's a high speed streak. You can see in the green circles there that there is some similarity between these structures and ours based on importance. And even if we look at the vortices, the ones that I showed you in the video, well, there's a bit of similarity between this region and that region over there. So you see where I'm going. There seems to be that the classical view kind of mixes up somehow, or the different classical views, they're telling different parts of the same story. It's like the story of the blind people and the elephant, that each of them was looking at a different part of the elephant, but nobody was looking at the whole picture. If you look at the comparison that we're going to make now in this figure, where we look at the spatial agreement between different types of structures, you're going to see how close the different blind people were to the full elephant. In the vertical axis, I'm showing you the percentage of coincidence between different structures. And the horizontal axis, the distance from the wall, the distance from the wing surface. And again, this is for the 3D objects, for each of the snapshots, how much they overlap, basically, and then statistics of that. The yellow line shows the agreement between the SHAP and the streaks. These are the things that happen close to the wall. And they have 90% agreement at one location, and that agreement goes to 0. So that means that these structures, these streaks, are very important in one particular region, and the rest of places, they're not so important. And by the way, for many decades, people thought that the streaks were everything in turbulence, and they were right, just in one part of your domain. If you look at the Reynolds stresses, which is this blue line over here, you see that there is about 50% agreement close to the wall, and about 60% agreement farther away from the wall. So, there is a decent agreement in different parts of the flow. Interestingly, this green line, which is the vortices, again, this is what people show you every time that they do a fancy visualization, like the one that I showed you before. It's only 15% agreement far away from the wall. So they're not so important, even if everybody shows it. And why people show that? Because you can see them. Sometimes the fact that you can see something in an experiment, in a simulation, does not mean that it's important. It's simply there. So by, again, interrogating the data, looking at the causal relations in the data, and again, this is very high-quality simulation data, so we are really capturing all those temporal dynamics. We can create a more complete picture. So what this shows is that the classically studied structures only paint a partial picture of turbulence. And if you put all of them together, you come closer to the full picture that we identify with nonlinearities, with causal mechanisms, and with different temporal and spatial scales, basically. So this is kind of like the ending part of the section where we identify the most important structures in the flow. And this is helping us to really reshape the way that we study turbulence, because we kind of have a fresh view on how to, avoid a little bit the physical biases and try to focus more on what the data is telling us, basically. So I promised you that there was going to be flow control, or I promised the people who gave me money. So let's talk about that. I want to reduce the drag. So the idea is, now that I identify what are the most important features in my 3D flow, I want to try to find ways to remove those features that are important. And to do that, of course, I mean, this is a very well-versed audience in ML. I have a high-dimensional problem that is chaotic and is changing dynamically. So obviously, reinforcement learning is a, well, natural choice to try, at least. And we were the first ones to try reinforcement learning to control turbulence some years ago. This is when it got published, not the year we started doing this. And I don't have to explain reinforcement learning to this audience, but I can just say that the agent, which is the neural network that we're going to try to train, is interacting with an environment, which in our case is going to be either a simulation of the flow or an experiment of the flow. And the key is that the agent is going to try different strategies, different control strategies, which in our case is going to be through jets on the surface of the wing. So I have my wing here. In some places, I'm going to blow air, and in some places, I'm going to suck air. And by doing that dynamically, again, because this is very chaotic, what I'm going to try to do is minimize the drag and the friction around the wing, basically. And this is something that, I mean, we have this is the first application of reinforcement learning. This is Luca Guastoni, a great former student of mine, who did that. And we have also a review paper on how reinforcement learning is used for flow control, which may be of interest to some people in the community and in this audience. So the idea is that we wanted to try reinforcement learning to control turbulence and compare with a classical benchmark. The classical benchmark, well, we were trying on this channel flow. So basically, this is a flat plate, and we're going to try to do blowing and suctioning there. We consider two cases, one in a small domain, so the computational box is smaller, that will make the physics simpler, and that for training the reinforcement learning agent is going to be easier. And then we're going to do transfer learning to a larger domain where the physics is more complicated, basically. And the classical benchmark is what is called opposition control. So in opposition control, what we do is that we have the wall here. We're going to sense the flow above the wall at a region where the fluctuations are very strong. And we're going to be looking at the vertical fluctuations. So if the flow is going up, we're going to put a velocity that is negative at the wall, so we're going to do suction. If the flow is going down, then we're going to blow. So that's why it's called opposition. This is a linear proportional controller, basically. And this, despite being very simple, this is 30 years old, by the way, it gave quite some reasonable performance in many cases, and that's why it's a good benchmark for us. And our expectation or our hope is that with reinforcement learning, we will come up with a policy that is something a bit more sophisticated than just opposing the fluctuations, something a bit more complex. And well, that's what we want to do. I want to also illustrate this with multi-agent reinforcement learning. I know that this has different names in the ML community, depending on who you talk to. But I will just say what I mean with multi-agent reinforcement learning. Essentially, we have our domain where I have an invariance in both the stringwise and spanwise directions. The flow is homogeneous. And of course, the flow is turbulent and chaotic, but statistically, in all those directions, it's doing the same. And I have all these pseudo-environments, which are copies of the same agent, where what I managed to do is to train in parallel, because each of those pseudo-environments is seeing a different instantaneous realization of the same physics. Statistically, it's the same physics, but they are different instantaneous fluctuations that all together would correspond to the same problem. So I can parallelize the training with these pseudo-environments. And the other thing is that because the reward is global, the reward is the drag reduction, in this case the skin friction reduction, over the whole wall, all those agents, all those pseudo-environments start to cooperate to achieve the maximum drag reduction, basically. So we did a lot of experiments where with single agent, meaning that each of these pseudo-environments has its own parameters, then each of them egoistically would try to maximize their local region and not achieve very good performance. But with a multi-agent, by exploiting the invariances and by achieving cooperative learning, then we got much better results in turbulent flows. And this is something that we also reported here in Nature Reviews Physics with experimental work, so both numerical and experimental, and it worked pretty well for turbulence. So look at the results yourselves, which we're going to see right now. So if we look at the drag reduction, and this is for a full channel, so for the large domain, The classical control, the linear proportional controller, gives me about 20% drag reduction, which is good. But the reinforcement learning gives me 30% drag reduction, so that's 50% better. So we basically come up with a much more sophisticated control strategy and a highly performing policy for my drag reduction. So in this case, when my reward is just the drag reduction, I get much better performance. I can also analyze the physics of this problem when the flow gets controlled. For example, here at the top, and I'm showing you here a joint probability density function of the stringwise fluctuations, so fluctuations in this direction, and the vertical fluctuations, fluctuations in that direction. So what you expect when you don't do anything to the flow, for a normal turbulent flow, is what you see at the top. Okay, so this is no control, where you have a predominance of this corner, the top left, and the bottom right corner. These two are basically the sweeps and ejections that I talked about when we were looking at explainability. So this is what happens when you don't do anything to the flow. In the second row, when you do the opposition, which is the linear control, and the opposition, what it does is to shrink the vertical fluctuations. That's what the control is doing. You have this linear control. But you can see that the flow doesn't really change so much. In practice, you still have the predominance of the top left and bottom right panels. So at the end of the day, sure, you reduce a bit the drag, but the flow does not really change. In the third panel, the reinforcement learning shows a fundamental change on the physics of the flow. So you first of all see that the predominance of those two quadrants is gone. Now we have a pretty even distribution of the fluctuations across the 4 quadrants. And more interestingly, what happens in the end is that you completely stabilize the streaks, which are the important structures that I mentioned before. Okay? So basically, in this case, what you can see with the reinforcement learning is that we are significantly affecting the physics of the flow in a way that we can really reduce the drag quite significantly. Okay, that's good. Now is where the fun stuff happens. So all the way to reach now the title of the presentation, Improving Control with Explainable Deep Learning. What if, in the reward, instead of just reducing the drag, what I do is reduce the important structures in the flow? And why would that conceptually make sense? Well, if we think about it, the drag is just the symptom, right? But the disease, the reason for that drag, is the turbulence. All these very complicated fluctuations, they increase the friction. So if instead of telling the reinforcement learning, look at this drag and reduce it, what I say is, these are the 3D objects that are causing turbulence, and turbulence is causing the drag increase, go after those 3D objects and see what happens. And that's a little bit what we try to compare here. The setup is the same. So we have a wall. We are measuring the flow above the wall, and we're doing blowing and suction. What I'm going to compare is different rewards for my reinforcement learning. So in blue, I'm going to show you the baseline, the linear control. In orange, the reinforcement learning, where the reward is the friction, what I just showed you a moment ago. There's not going to be any surprise with these two because you have seen the results already. In green, I'm going to remove the Reynolds stresses, one of the classical extractors. In red, I'm going to remove the streaks, another of the classical ones. And in purple, the SHAP-based, importance-based objects. So let's see what the results look like. Over here. So in the top panel, I'm showing you the drag reduction as a function of time. So you set up the control, then you see what the flow is doing. In blue, you can see the 20% drag reduction of the linear model. In orange, the 31% drag reduction, where the reward is the reduction of the drag. And in purple, you can see in this arrow over here, this is what happens where the reward is the SHAP, is the importance-based extractors. You get 5% higher drag reduction than the naive minimization of the wall shear stress. More importantly, you get much lower fluctuations over here. You get a much more stable control because, once again, you're just surgically going after the most important features in your flow. This is very interesting from 2 points of view. The first one is we beat the reinforcement learning. So by informing the reward with physics of what's important in the flow, we get a higher drag reduction. But also, we show that the other classical structures, the Reynolds stresses and the streaks, they give me less drag reduction, which means that they were less important for the turbulence than ours. So we're basically accomplishing two things here. We're confirming that our SAP-based methodology identifies truly important features in the flow. And second, we're also showing that by informing the reward with physics, we get much better performance. So this is actually quite exciting when I saw that it was working. In fact, the cost of the control, which you can see in the next slide, if it works. Yeah. So the cost of the control has to do with the pumping power of the jets. If you have to blow more air, it's going to be more costly. You can see that the orange line has twice the cost of the purple line. So it's much more costly to do the blind, naive reduction of the friction, because in the end, what the reinforcement learning for friction reduction does, in practice, is a bang-bang control. It's just trying to destabilize the near wall and the structures, but without too much targeted control. The SAP-based control, what it's doing is going after certain features in your flow in a much more selective way. So you get half of the cost of the control, and if you look at the net energy savings, this is a quantity that is important when you look at transportation systems, because not only do you want to reduce the drag, you also need to see the cost of your control. If you reduce the drag a lot, but you spend a lot on your control, then you didn't do anything. So the net energy saving is a quantity that takes into account the drag reduction, but also the power that you put in to achieve that drag reduction. Then the difference between the SAP-based control and the naive drag reduction gets even higher. We have 5.5% difference. And if we put this in an experiment where you have more actuators and much more blowing and suction, then this difference gets even higher. So once again, this is quite promising in terms of being able to inform pretty good reinforcement learning strategies by identifying important features in your flow. Okay, so we're pretty excited about this. And to conclude, I want to show another cool example of how we can apply this to more complex geometries. This is another wing. Before I was doing a lot of ML, I was doing a lot of these simulations of turbulent wings. And now the idea is that I want to put my reinforcement learning to control a portion of the wing and reduce the drag. So not on a flat plate, but on a real wing. And of course, this is me being very optimistic. I'm just going to solve the problem. But there's at least three fundamental problems with this setup over here. The first one is the wing only have one invariant direction, which is this one. The channel before had two invariant directions, which means that you could accelerate the multi-agent training quite a lot. But here you only have one direction to have pseudo environments and speed up the training. That's one limitation. Second limitation is in the channel, you're just simulating one set of scales. But here, because the flow is going in this direction, the stuff here is much smaller than the stuff over here. So if I want to control the flow here, I still need to simulate these things, which are much smaller, and therefore they require a much smaller time step. So I need to integrate for many more time steps to reach the same place because of the scale disparity that you have in the wing. Second problem. Third problem, simulating a wing computationally is much, much more expensive than simulating just a channel, because in the wing you have the curvature, you have the far field. It's a much more complicated geometry. Therefore, and you know that reinforcement learning is very expensive because you need to train many episodes, many initial conditions, and stochasticity, so it's really very expensive. So these optimistic ideas seem to be a little complicated, but then we came up, and this is something together with my students, Junin Wang and Paul Suarez, and Junin Wang was crazy enough to follow me here from KTH. We came up with this idea. So what if, instead of training on the wing, we would just take a block of the wing, like this section over here, we'll take the conditions on that portion of the wing, and then take a channel, make the channel very big, so we have a lot of multi-agent, many agents, many pseudo environments to speed up the training. I do all my training in a channel, mimicking the local conditions that you have in the wing, and once my training is done in a channel, then I do zero shot and I go back to the wing and deploy that directly on my wing section. Now this has several advantages. The first one is I increase the number of pseudo environments, because in the wing I only have one homogeneous direction, in the channel I have two, and I can make them as big as I want. So basically, I increase by a factor of 20 the speed up of the training, because I can train 20 times faster. I only need to simulate a range of scales, not the whole range of scales, which means that I can have a time step 3 times larger meaning that I make my simulation 3 times cheaper. And a channel, as I mentioned, is computationally much cheaper than a wing because you only need to resolve the region close to the wall. You need to resolve the far field and the pressure side and all of it. So basically, it's 176 times cheaper to simulate a channel than to simulate a wing. So basically, by using these channels as a surrogate for the local physics of the wing, doing all my training in that channel and then doing zero shot back to the original wing, I train 60 times faster and 10,500 times cheaper than if I were to train the same reinforcement learning agent in the whole wing simulation. And does it work? Spoiler alert, it does. This is ongoing results, so this is preliminary results basically. But when we train, and we took 2 regions of the wing, this is upstream, so at the beginning of the wing, and this is at the end of the wing basically, just to try different parts. If I train in my channel the reinforcement learning, and then I do zero shot to deploy the same policy in the wing, I get about between 25 and 30% drag reduction. And the classical method, which is the linear proportional controller, is about 20% drag reduction. So you can see that we still perform way better than the classical approach by using this domain transfer strategy and basically taking advantage of all the student variants that you can have, all the student environments that you can have in the channel geometry. So this is something that we believe is pretty cool, and we're developing much more to be able to deploy to larger scale situations. And this is just a little summary of other applications where we really use reinforcement learning to control complex flows. This just came up in Nature Communications. This is a turbulence separation bubble. So basically, when a wing is at a very high angle of attack, you can see separated flow. And with separated flow, you can lose lift and have very severe stability problems. So with this, we showed that reinforcement learning can control that separation region much better than classical methods, which are typically based on periodic control. So this one, check. With cylinders at progressively higher Reynolds numbers, we also achieve much better performance in terms of drag reduction than with linear periodic control. So we published that in Communications in Engineering. And this is a heat transfer application. This is a 3D rate convection problem where the reinforcement learning completely rearranges the convection cells in such a way that the heat transfer gets minimized. So we also show the applicability of our reinforcement learning methodology to control heat transfer in quite complex engineering problems. And that's pretty much what I wanted to talk about today. This is a summary of my presentation. I showed you that using SHAP and explainability to identify important features in our flow is interesting and promising approach to look at problems in a kind of unbiased way. So we really identified important structures based on this explainability framework. Second, we use reinforcement learning for flow control. And because this is a high-dimensional dynamic problem, reinforcement learning was able to find quite good strategies for control. And the most exciting part is that by combining the interpretability, so the important structures that we find in the flow, with the reinforcement learning, so by informing the reward with those important features, then we get the best performance in terms of drag reduction. All the codes and all the data are available in this repository. So just use this QR code. You can find everything there. I also have a YouTube channel where you can find a lot of material and lectures and stuff. So if you're interested in these topics, you can access a lot of things there. And for now, that's all I have for today. I'll be happy to take your questions.
I'll start with a question, and thank you very much for your talk, Ricardo. So one question I have is this SHAP, application of SHAP to these surrogate models for fluid simulation seems like a very promising direction. Do you see it being applied to other areas? If so, which areas do you think is most suitable for applying the same concept?
Yeah, that's a very good question. I mean, I think that in any high-dimensional optimization context, and there's some research on causal reinforcement learning, where you may be able to optimize with these features and in many different contexts. This is for physics discovery, what we have been using here, but I can see applications of this for instance, to look at other problems, like what are the flow features that have the highest acoustic impact on your flow, or the highest mixing, so you can fine-tune different applications. And then another area where I believe there is potential is modeling. So we can maybe target those important features in your domain. So those are the essential ingredients in your domain, and try to, with reinforcement learning, with some optimization, make sure that those ingredients are in your domain, at least those, because those seem to be the ones that matter the most. So I would say for optimization in general and for modeling, I see some possibilities too. Thanks. Thank you.